sound. So we've talked about image processing. We haven't talked about sound processing, which actually has a lot of useful scientific applications, at least in certain fields. So it turns out Python actually now has some pretty good mechanisms for dealing with sound. So we'll go over a few of those. Now, if you're dealing with sound, there are some basic properties you have of any sound object. Basically, a sound is just a recording of some amplitude change over time. It's the waveform of the pressure wave for the sound. Now, when you store that, you have to decide what your number representation is going to be. How many bits of precision will you have when you store each of those individual samples? In many cases, if you're, say, recording something from a microphone, that will depend on the physical hardware that you have available. The physical hardware may only be able to provide 8 bits of precision or 12 bits of precision, whatever. Generally speaking, low-fidelity microphones will give you about 8-bit precision, and high-fidelity ones will give you 16-bit precision. There are some very rare ones which give you 24-bit precision. And how much you really need to have high-fidelity audio is still kind of an open question. The way the ear hears is in frequency space, not real space. So the question of how many bits you need to use in real space to adequately represent the signal in the complex space, the Fourier space that the human ear hears in, is not easily defined. So you will find audiophiles who will swear to you that 24-bit or 32-bit audio processing is absolutely necessary to maintain proper sound quality. But most people would listen to a 24-bit sample and even a 12-bit sample and not be able to hear the difference between the two. Audiophiles will insist that they can, and maybe they can even prove it in certain situations. Anyway, so the number of bits that you use in your representation is open for debate. 16 bits would be sort of typical, so sort of CD quality sound would be 16-bit samples at a sample rate of 44.1 kilohertz. So this was defined by the audio CD standard back in the early 80s, something like that, when it was first being defined, and has basically become this sort of the standard frequency that's used for audio sampling ever since. This is related to the highest frequency that the human ear can register. A healthy young person's ear may be able to hear frequencies, up in the 10 to 20 kilohertz range. 44 kilohertz sampling is sufficient to represent frequencies as high as 20 kilohertz, but not accurately. It can represent 10 kilohertz signals very nicely. And if you take the computational math class in the next couple of terms, if you're in QCB, you will, then we'll talk a little bit more about sampling and that sort of thing there. But anyway, 44.1 kilohertz is sort of the standard. Then the last thing is the number of channels, right? Do you have a monaural signal, stereo signal, or surround sound? The way surround sound is generally stored is sort of a strange thing, so we're not going to get into that today. But mono versus stereo would basically be you have one list of numbers versus two lists of numbers. It's just that if you have 5.1 channels, it isn't as simple as just having 5 lists of numbers. It's a much more complicated situation than that. Then the last thing is how you represent the file. You probably all have MP3 files laying around still. AAC is another format / representation. MP3 is a lossy file format. When we talked about JPEG compression of images, MP3 is like that. It's a perceptually lossless format, which actually occupies a lot less space, whereas FLAC is a lossless compression scheme, which gives you exactly the bits that were as they were originally sampled. So there are various representations in codecs. Thankfully, you don't have to worry about most of these issues when you're doing audio processing. The practical side of dealing with the files doesn't require you to be knowledgeable about these things. You might need to be concerned with how much compression is going on and whether that's going to impact the sound quality and that sort of thing. So there are three modules that I will recommend here for dealing with audio files. So Python for many years has had good libraries for reading and writing sound files and doing manipulations on them. What it hasn't had good libraries for is reading from microphones and writing to speakers. So playing sounds and recording sounds. Python has often had platform-specific modules, but they haven't had many good modules which are cross-platform and work on all the different computers. There is now a library called Sound Device, which seems to actually be pretty mature and usable, which you can just pip install Sound Device and get it, and it'll work on Linux, Mac, and Windows. I won't guarantee it'll work in every situation, but everything I've tested, it's worked pretty well. So we'll talk about that a little bit. There's Sound File, which is a related module, which is good at reading and writing a variety of different file formats. One trick is, though, they do not support MP3 because of patent issues. PiDub is another audio file I/O utility, and this one does support MP3 files by using an external package, so they don't have to directly worry about the patent issues themselves. All right, so PiDub, we'll start with that one. Is pretty easy to use. Let's just start with this. So we'll import the module. We will read from an MP3 file that I have stored on my disk here, and then we just display the song. And when you do this, as soon as it finishes, there we go, it'll actually, in Jupyter, will give you a little play widget. So it can read an MP3 file and play it. You can easily get clips from the file. So this is in milliseconds. So this is 4.6 seconds to 6.5 seconds in the file. Do that. And now X is a clip from the file. We can extract the raw data from the file using this get array of samples method. Now this is a stereo file, so let's go ahead and so I'm just getting 0.1 seconds out here, so it won't be too long. So if we look at len of data, we'll see that this has 8,820 samples. All right, now why is this? This was 0.1 seconds that I pulled out. And we're sampling at the standard 44.1 kilohertz. So for every second, we should have 44,100 samples. But you can see we have twice as many. Well, that's because it's stereo. And the way this is encoded is it's basically the sample for left, sample for right, sample for left, sample for right. So if we look at data, just the first few elements, you'll see that that this is, this is obviously not a single sequence, right? Minus 474, minus 742, minus 402, minus 688. That would be a really, really high frequency sound if we listened to it. But if you look at minus 474, minus 402, minus 284, minus 294, that's a sequence. And here, minus 742, minus 688, etc., that's a sequence. So if we instead said data 50:2, so we're only going to take every other element, then we can get out a nice sequence just for one channel. Or if I started with element 1, I could get out a nice sequence for the other channel. Okay, now you'll notice that these objects that we get from PiDub are array objects. These aren't NumPy array objects. These are native Python array objects. You remember I mentioned that Python had an array class, which was kind of like a very primitive version of NumPy arrays built in. So that's the class that will return by default. You can very easily convert that into, I thought I had that in my example, but anyway, fine. We just import NumPy as np, d equals array, d equals np.array. So we can just initialize an actual NumPy array from the Python array. And if you need to do the more complicated sorts of things that you can do in NumPy with your data, you can easily do that. Okay, so that's all I'll say about PiDub. There are a number of other methods available in PiDub. So if you want to write stuff back to files, so if you want to extract a clip and then write it to a file, that's very straightforward to do. Let's talk a little bit about Sound Device. So Sound Device is actually very nice. It allows you to simultaneously use input streams and output streams on the same machine. So technically you could play a sound at the same time you're recording sounds, which is a capability that a lot of packages like this wouldn't have. So let's just start out with the output stream. Oh, sorry, I'll need to import it first. Do it here. All right, so we're going to open an output stream. We have to tell it what sample rate we're using. We're just going to use the default here. And I'm just going to use one channel. And we have to tell it the type of data that we're going to be giving it. int16 is the default type for most audio data. If you have an 8-bit sample file, then obviously it'll be 8-bit, not 16-bit. But by default, it's not an unsigned integer, it's a signed integer, so the values go from minus 32,000 to 32,000, basically. Okay, now we need to have some data to deal with here. So let's go ahead and we've got our data that we have from our sampled sound here. Let's extract a different subset. So let's see. Let's say d2 equals np.array song. We'll go ahead and use the range that we were using before here. Oops. Okay, so I'm going to extract a clip from the song, and I'm going to convert that to a NumPy array. There we go. All right, so now D2 is our data. Let's see what happens when we play it. Sound data 0. Oh, sorry, not sound data. This is D2. Okay, what happened there? Well, I didn't take every other sample. So that's both the channels of the stereo being played in a single channel. So it has twice as many samples, so the speed is slowed by a factor of 2, and you're getting this mix of two channels together. So we'll take every other element. Let's put it like this. I think that should work. All right, we can also do inputs. So let's do this. We can make an input stream. And here I'm going to, again, it'll have a sample rate of 44,100. And I'm going to read 44,100 samples, so basically 1 second. So I'll run it once just to get it initialized. And then, hang on, we'll just run this part. I don't need to create the stream object again, and we'll actually. Oops, why is that? Oh, sorry, that's fine. Then we'll try again. Testing. And now we can play back what we recorded. This is where I actually have to, actually 0, I think. I have to say that, and I'll explain that in a second. Testing. Okay, so we recorded the sound, played it back, and if we look at sound data, you'll see that it's an array. It's a tuple containing an array and a logical value. And that is just returning some aspect of whether there's more data available from the stream or something like that. It's not something we have to worry about in this context. Anyway, we have a nice array, a NumPy array, containing all of the numbers from that sample that we just recorded. We could do something like this. We could visualize the sound wave that were recorded. So you could actually build, if you used a few of the GUI tools that we talked about last time, you could actually build a nice little sound editor using some of these tools pretty easily. So anyway, that's all of the sort of demonstration I'm going to do about sound. I have something in mind for Monday, which we'll see if it works or not. So I'm giving you a quote homework assignment. I'd like go ahead and install Sound Device on your machines before Monday, and we'll see if we can get something neat to work.